All right, so this is chapter 2 on describing change rates, and this is section 2.2 on measures of change at a point, and it's graphical. And due to the fact it's graphical, I have to kind of have a different format for the slides. Hopefully this will work. All right, so the AROC, remember, average rate of change of a quantity, is a measure of the change in that quantity over a specified interval. Now, the change occurring at a very specific point can also be measured, and one measure of the change of a quantity at a specific point is called the instantaneous rate of change. Now, the AROC, though, measures the slope of a secant line between 2 points. So if we look at our table here, this is a table of data. This is our curve that it represents after we've done a model. And our AROC is basically, from, this point 1, to this point here, which is point 3, we can get this average speed of 64.6 miles per hour, okay? And that's the slope of that secant line is what it is. But what's going to happen is we want to find the instantaneous rate of change, and that's going to measure the slope of a graph at a single point. So we're going to look at it just the point. And so what we can do is we have to have a slope of a graph of a function that can be defined at a point if the function is continuous and smooth. So basically, it can't have any sharp corners. And so that's kind of what we have for our graph for the speed here. And so then what we're going to do is if we zoom in on any of those points, what we're going to see is this here zoomed in point. And if we look at that, at this point, when it's zoomed in very, very, very close, this is like very minuscule, but it's, magnified to a great extent. So it's very little distance on each side here, but you can look and it looks pretty linear. And so that's kind of looking like the local linearity is what it's called at that point. So that's how the linearity looks at this point on each one of these. Okay, and now what we're going to do is we're going to move that into something called a tangent. And the tangent is a line, and if you can see here, it's the dotted line right on the point. So it doesn't touch the graph, it's above the graph in this case. And here, that's the inflection point, so it's kind of going through, and this one is below the graph. So it's not really going through the graph except for this one where the inflection point is. And it matches that tangent line, basically that local linearity. Okay, and so this tangent line has the same slope as this local linearity does at the point. And so for each of those cases, that's what we see. Now, if we want to have some Latin, the word tangent comes from tangere, which means to touch. So it's just touching the curve. It's not, intersecting it and going through it at any point. It's just very, barely, barely touching that curve. Okay. And it's touching it at that one single point. So very, very minuscule piece. And so and that point where it touches is actually called the point of tangency. So, so we have that tangent line, which is the line that kind of goes the same slope as the local linearity, and it touches exactly at that point of tangency. Okay, so I'll stop there and then we'll continue on with the next part.